This video covers section 3.4 on zeros of polynomial functions. In this section, our goal is to find all zeros of a polynomial without being given a zero or a factor. So it's similar to the way section 3.3 ended, but in all those problems at the end of 3.3, they gave us some information to help us get started. So now we're going to learn how to do the entire problem without being given a place to start. So our first theorem is what we call the rationals zeros theorem. It's going to give you a way of identifying the possible rational zeros of a polynomial by looking at the leading coefficient and the constant term. So if you have a polynomial, we talked about the leading coefficient being the coefficient of the highest power of x, and the constant term is the term that doesn't contain a variable. So if you look at those two terms, you can figure out the list of the possibilities of any zeros that are rational. So if we can identify those first, we'll be able to go from there to figure out the rest. So the list of possible rational zeros is found by writing down the factors of the constant term, in other words, all numbers that divide evenly into the constant term, divided by all factors of the leading coefficient, meaning all numbers that divide evenly into the leading coefficient. So you create fractions out of factors of the constant term divided by any factor of the leading coefficient to get the list of possible rational zeros. So this first example, we are simply just going to write out that list. F of x equals 4x to the fourth minus x to the third plus 5x squared minus 2x minus 6. So in this example, our leading coefficient is 4 and our constant term is negative 6. So this is abbreviation for possible rational zeros. Would be positive or negative 1 divides evenly into 6, plus or minus 2 divides evenly into 6, plus or minus 3, and plus or minus 6. So it's essentially all ways you can multiply two numbers and get a 6. A 1 times a 6 or a 2 times a 3. The denominator should be all factors of 4. So plus or minus 1, plus or minus 2, and plus or minus 4 are the only numbers that divide evenly into 4. So this is the format of what a possibility of a rational zero would look like. If it asks for the list, the complete list, you would want to write them all out. So plus or minus 1 over 1 is 1, 1 over 2 is 1/2, and 1 over 4 is 1/4. Then you move on to the next possible numerator. 2 over 1 is 2. 2 over 2 would be 1, and we already have that listed, so we do not need to list it again. And 2 over 4 would be the same thing as a 1/2, and we already have that one listed, so we're not going to list it again. Then you would have 3 over 1, which is 3, 3 over 2, 3/2, and 3 over 4, 3/4. And then finally 6 over 1, which would be 6. 6 divided by 2 would be 3, and that's already in our list. And 6 over 4 would be 3/2, and that's already in our list. So this would be the complete list of possible rational zeros. Meaning, if f of x has any rational zeros, meaning zeros that can be written as a fraction of integers, so they're not square root values and they're not imaginary numbers, they must come from one of these numbers. So any rational number not listed is not possible. All right, so a few just comments about properties of polynomial functions in regards to finding the zeros. If f of x has degree n, then counting any multiple roots separately, f of x is going to have n roots. So the degree tells you how many roots or how many zeros there are altogether. If a plus bi is a root, then a minus bi is also a root. In other words, imaginary roots must come in conjugate pairs. You cannot only have one. You must always have its conjugate with it. So there's always an even number of imaginary roots if there are any at all. That also goes for roots that involve a square root. You would only get a square root by taking the square root of something, meaning plus or minus, so it would have to have 2. Each root corresponds to a factor. So if it has n degree, meaning n roots, we can write it as a product of n factors. All right, so if I need to find all zeros of a polynomial, step 1 is look at the degree to identify how many you're looking for. Right, so if I know I'm looking for 4, then I'll know whenever I have found all of them. Step 2, list the possible rational zeros. That's your starting point. Step 3, use synthetic division to identify at least one or more rational zeros. So if you have a list of rational zeros, you can start synthetic division by checking to see when you do synthetic division with those numbers when you get a remainder of 0. Because remember, if you get a remainder of 0, then that means you found a factor which leads to a 0 and you can move forward. Okay, this is the step where a graphing calculator may be helpful. Okay, if you have this long list of rational zeros without a graphing calculator, you're just going to have to start trying them until you find one. But if you have a graphing calculator, you could graph the function and see on the graph where it's touching or crossing the x-axis and know which ones are going to work ahead of time. Step 4 then is use the quotient from step 3. Once you've done synthetic division and found a 0, use that quotient to help you find any remaining zeros. So the first example, f of x equals 2x to the third minus 5x squared plus x plus 2. If I needed to factor this, I can't do it without knowing what we're talking about in this section because this does not factor by grouping. All right, so if it's a degree 3, that means I'm looking for 3 total zeros. So my possible rational zero list, remember factors of the constant, so factors of 2, so plus or minus 1 and plus or minus 2, divided by factors of the leading coefficient, which is also 2, so plus or minus 1 and plus or minus 2 on the bottom. So 1 over 1 and 1 over 2, and then 2 over 1, and then again 2 over 2 is 1 again. So plus or minus 1, 1/2, and 2. All right, so if I don't have a graphing calculator, I'm just going to start trying one until I at least find 1. If I can find 1, my result will get me down to a second degree, and any second degree polynomial we know how to solve. We know how to solve quadratic equations. So that's kind of tell you how many you need to find on your own. If it's degree 3, you need at least 1. If it's degree 4, you'll want at least 2, etc. So I would start with my list. So I'm going to test the first number in my list, which is 1. So I'm going to put a 1 out here, line up my coefficients of my polynomial, and do synthetic division. So I drop down the 2, multiply as a 2, and it would go here, add as a negative 3. Multiply negative 3, add as a negative 2, multiply as negative 2, and add as a 0. So I got lucky here. I found one right away, right? I got a remainder of 0. So the remainder is 0, so that means x equals 1 is a factor. I'm sorry, x equals 1 is a 0, so x minus 1 would be a factor. If the remainder was not 0, then I would start over and use negative 1 out here and see what happens. If I get a remainder of 0, then I found one and I move on. If I don't, then I move on to the next number in my list. So you can kind of see how this can get time consuming if 1 doesn't work and you don't have a graphing calculator. All right, so if I know x equals 1 is a 0, that means x minus 1 is a factor. And then these numbers represent the quotient 2x to the second minus 3x minus 2. So once I get to this quadratic, I should be able to solve. This one is factorable. It factors into 2x plus 1 and x minus 2. If it was not factorable, you could still solve it by using the quadratic formula. All right, so either way, we end up with 3 zeros, right? All 3 of them. X minus 1 gives me the 0, x equals 1. 2x plus 1 leads to the 0, negative 1/2. And x minus 2 gives me the 0 of x equals 2. Okay, this next example is a 4th degree. We're going to use the calculator on this one to kind of show how that would be helpful. So we have x to the 4th minus 2x squared minus 16x minus 15 equals 0. So here we have a degree 4 polynomial, meaning we're looking for 4 zeros. My list of possible rational zeros. Factors of 15. 15 is my constant term, so plus or minus 1, 3, 5, and 15. Divided by factors of the leading coefficient, which is a 1, so that's just plus or minus 1. So 1 over 1, 3 over 1, 5 over 1, and 15 over 1 are just these numbers. All right, so I could start the way I did before and try 1 and see if it works, and then try negative 1, etc. until I found one. Or I could use my calculator. Okay, so this is a TI-84. So if you turn on your calculator, if you have a TI-84 and you press this Y equals key right here, it will bring you to a screen where you should see Y1, Y2, Y3, etc. This won't be here yet. All right, so once you get to that screen, you're going to type in your polynomial here. So my polynomial was this. All right, so the X key on your on this calculator is right here, right next to the green alpha button, this key that says X, T, theta, and N. That's your variable key. So if you press that, you'll get X. Then the caret button is over here to the power, raised to the power. So press that and then type in your 4. If it's a newer version of the calculator, you'll have to use the right arrow to arrow out of the exponent. All right, then you're going to come down here. Subtract is right here, minus 2, and then your variable key again, X to the power 2, arrow out of the exponent, minus 16x minus 15. Make sure you're using the subtraction key here and not the negative in parentheses down here at the bottom. This is just if your leading coefficient was a negative number, you have to type like -2 or something, that's when you use this one. In between terms of a polynomial, you need to make sure you're telling it to subtract. Okay, those are different, they have different meanings on this calculator. All right, then you're going to press enter. Okay, then if you press this key right here that says graph, you should end up with a graph. If you're not in, so this is if you're just in a regular standard window, which is the default, this is what you're going to see. If this is not what you see, to change your window, you can press the window key right here, and you can adjust your X-min, X-max, Y-min, and Y-max. Just I would start it at -10 to +10 in both. Or you can press zoom, and if you hit zoom and then press 6 that says Z standard, it will take you to the standard 10 by 10 window. All right, so here's my graph that shows up. So I can see on this graph that I'm crossing right through my x-axis here at -1, and then at 1, 2, 3, I cross through again. So I can look on the calculator and tell, well, -1 and 3 both are in my list, right? So I can tell here that those are the ones that are going to work. So I'm not going to bother trying any of the others. Okay? So from the graph on the calculator, we can see that -1 and 3 are zeros. Okay, I still have to do synthetic division because I need to find the other 2, right? Also, notice I'm only seeing 2 zeros here, and I'm looking for 4. Remember, only the real zeros are visible on the calculator. So if you're needing 4 and you only see 2, it could be, or it's probably very likely that the other 2 are imaginary, and you're not going to see them, and you're not going to be able to figure those out from looking at the calculator. It's also a possibility that you might see 4, but maybe only 2 are rational. Maybe the other 2 are irrational. All right, so just keep that in mind. All right, so -1 and 3 we could tell from the calculator. So I'm going to line up my coefficients of the polynomial, start with the -1, do synthetic division. Drop down the 1, multiply -1, add is -1, multiply is +1, add is -1, multiply +1, add -15, multiply +15, and add is a 0. This should not be a surprise because we already looked at the graph. So I just kind of check mark that yes, I verified it. All right, so notice this line here would represent a 3rd degree polynomial. Okay, so if you found more than one, we're going to take the other one we found, which was 3, and we're going to work on, we're not going to start over, we're going to go on this line. Because if this is 3rd degree, if I do synthetic division on that line, my next line will be second degree. That is my goal, to get down to at least a second degree that I could finish myself. All right, so we would drop down the 1, multiply as a 3, goes here, add as a 2, multiply as a 6, add as a 5, multiply as 15, add as a 0. So we verified that one. So the x minus 1 means x plus 1 is a factor. The 3 means x minus 3 is a factor, but these numbers are what I have to come up with in order to find the 2 that I can't see. So 1, 2, and 5 would be my 1x squared plus 2x plus 5. This one does not factor, right? So I'd have to solve it by the quadratic formula. By the way, these are just going to lead to the ones you already knew. All right, so here we would get negative b plus or minus the square root of b squared minus 4ac all over 2a. And then cleaning that up, 2 squared is 4. 4 times 1 times 5 is 20, so 4 minus 20, that's negative 16. Square root of negative 16 is 4i. And then we're going to split up negative 2 over 2 plus or minus 4i over 2 is negative 1. For some reason that 1 did not scan, so that should be negative 1 plus or minus 2i. Right, and that makes sense that they're imaginary because they were not visible on the graph. So the list of all 4 zeros are the negative 1 and the 3, and then the negative 1 plus 2i and negative 1 minus 2i. All right, our last problem here is working backwards. They are going to give us some information about the degree and the zeros and maybe a function value, and we're going to build the polynomial. So find a polynomial with given degree and zeros. So it says that the degree is 3, so there should be 3 total zeros. Zeros given are 1 and 3i, so we're only given 2 of the 3, so we'll have to make sure we know how to find the one that they don't give us. And then we're given that f of 2 equals 26. So our first step is to list all the zeros, including any that we were not given. So we were given 1, we were given 3i, but if there's a degree 3 polynomial, we have to have a third 0. So this is where that conjugate property comes into play. We can't only have one imaginary. So if 3i was given, automatically negative 3i would have to also be a 0. That's the conjugate. All right, so now that we've got them all listed, we can build our factors. So 1 was a 0 means x minus 1 is a factor. 3i is a 0 means x minus 3i is a factor. And negative 3i is a 0 means that x plus 3i is a factor. Okay, so in other words, x minus the 0, right? X minus the 3i and x minus the negative 3i. We can build factors. All right, so our polynomial then is going to be the product of all these factors. I'm going to multiply them out, but I could have a coefficient by itself sitting in the front, and I'll have to account for that to figure out, right, using this information, what the a value might be. It's not assumed that a is always a 1. So our polynomial could have a constant a out in front times all of my factors. So the next step is to multiply this out. So if you have conjugate factors, meaning imaginary factors, you're going to multiply those together first. So we're going to leave the a and the a minus 1 here, and we're going to start by FOILing out these two. So x times x is x squared. X times 3i is 3ix. Negative 3i times x is negative 3ix. And negative 3i times positive 3i is negative or minus 9i squared. Notice the middle terms cancel out because they're opposites. And then this n term that has an I squared, there's a definition of I squared. I squared always equals the number negative 1. So this is negative 9 times negative 1, which is plus 9. So if these drop out, and this means plus 9 on the end, all you have left inside of there is x squared plus 9. All right, now we're going to multiply that by the x minus 1, so just FOIL. X times x squared is x cubed. In the middle you get minus x squared. On the end you get plus 9x, and then on the last two terms you get minus 9. All right, and now we're ready to try to find our value of a. So we were told up here that f of 2 is equal to 26. So once we've gotten all this worked out, we're going to plug in an x value of 2. So all these x's we're going to replace with a 2, and then that means that the f of x, the other side, should equal 26 when I do that. So I'm going to plug in 26 over here and a 2 for all the x's, and then I'm going to solve for a. So 2 to the third is 8, minus 2 squared is 4, plus 9 times 2 is 18, minus 9. 8 minus 4 plus 18 minus 9, all that cleans up to be 13. And then I can divide both sides by 13 and get a value to be 2. So I can come back up here where I had my polynomial before I plugged in my numbers, and I can plug in what we got for a, and then just distribute it through the rest. So 2x cubed minus 2x squared plus 18x minus 18. That is the end of section 3.4.